All right, we have been working with, oh, hi, how are you doing? Sorry, didn't mean to not greet you. Okay, so we've been working with Pythagorean identities and reciprocal and quotient identities inside and out, and we're finally going to start looking at what are some others. And then I'm going to throw a bunch at you in the next 3 days. So we're going to start today. We're going to do sum and difference identities. Now remember, identities are just a way of showing relationships between different trig functions. So we're going to look today at what happens when you are adding or subtracting angles together. For instance, what if I am doing the cosine of a 45 degree plus a 15 degree? Can we agree that that's the cosine of 60 degrees, right? I don't know why am I breaking it apart? It's just the cosine of 60, yeah? Okay, so what if it's given to me like this, though, and maybe not quite as straightforward? Can I just distribute here? Would that work? Okay, so in our calculator, we would try this. Now, a couple of these I know off the top of my head. I know that the cosine of 45 is just root 2 over 2. I know that the cosine of 60 is a 1/2. And if I did the cosine of 15, which I don't know, change mode, got to be in degrees. Okay, so if I did the cosine of 15, I get, interesting, I get a 0.96. Okay, now think about that. Does that make any sense whatsoever? And root 2 over 2, I'll just we probably have done this before, but if you don't know that root 2 over 2 is 0.7, does this make any sense? Does 0.707 plus 0.965 in any way equal 0.5? No, it does not. No, we cannot distribute. Do not do that. This right here, cosine is its own operation. It is not, when you see it like this is not multiplication happening here. We do not distribute trig functions. Big no-no. So every time you look at that and you think that, like slap your hand or something. I don't know. Don't do it. Don't distribute. Instead, we are going to go use these new identities. We have some identities that are actually valid. They're called the sum and difference identities. So, and it works for sine, cosine, and tangent is what we'll be doing this with. And so if you're taking the sine of two angles that are added or possibly subtracted, these are my two angles, alpha and beta, what you do instead of distributing is you set up this format. You take the sine of whatever this first angle is and you multiply it by the cosine of the second angle. And then this plus or minus right here just means do exactly the same thing you were doing over here. So if this was a plus, this is a plus. Then you switch it around and you do cosine of the first angle and sine of the second angle. And if you do that computation, that will be a legitimate answer. Okay, cosine, let's look at what its identity is. Instead of the pattern up here, look at this pattern. We do cosine of the first, cosine of the second. And then look at this notation. That means do the opposite of whatever was over here. So if this is a plus, you'll do a minus here. And then you do sine of the first, sine of the second. Okay, tangent, you can kind of follow through. Tangent of the first, tangent of the second, keep the sign. Down here, you're going to have a 1, and then change that sign, and now you're multiplying those same two things you were adding up there. All right, let's jump in and try one. And just for fun, I'm going to jump in and give you radians, so you have to think a little bit harder about it. All right, I have to come up with two angles that add up to 7 pi over 12. Okay, well, I mean, nothing jumps out at me other than, I guess, other twelfths, right? So I could do 3 pi over 12 plus 4 pi over 12. Or I could do 2 pi over 12 plus 5 pi over 12. Or 1 pi over 12 plus 6 pi over 12. Yeah, that's the gist of it right there. So which of these do I use, or could I use any of them? Well, here's the thing. I eventually am going to have to be able to take the cosine and the sine of these values. So I don't want to do things that I'm not going to ever be able to find the cosine and sine of from my unit circle. So my hint here is that you want to pick fractions that will reduce. For instance, pi over 12 doesn't reduce, and I don't know what the cosine of pi over 12 is. Now 6/12 does. That would reduce to pi over 2. I know pi over 2, that's like a 90 degrees, right? I can do sines and cosines. But if this one doesn't reduce, this is not going to work. 2/12, that would reduce to pi over 6. That's on my unit circle. I could do that. But 5/12 does not. So that doesn't help. 3 pi over 12 and 4 pi over 12 both reduce. This reduces to pi over 4. This reduces to pi over 3. Those are both on the unit circle. This is the version I need. So again, my hint, select fractions that will reduce. You've got to have both of them be able to reduce. And I will always give you something that will reduce to the unit circle. All right, so I'm going to write it like this for your notes. So you don't necessarily have to have that there. I'm going to write 3 pi over 12 plus 4 pi over 12, which I then would reduce to pi over 4 and pi over 3 because those are the things that I know on my unit circle. All right, so that's what I'm using. I'm going to find, when it says here, find the cosine of 7 pi over 12, I'm doing this right here. I'm going to break it down to pi over 4 plus pi over 3. And that's how I'm going to write 7 pi over 12. And I should clarify, I am finding the exact value. So this is not something I'm going to my calculator on. I want the exact value. So following the identity from the previous slide there, you're going to go cosine of the first angle, cosine of the second angle. And then it's a minus plus, which means do the opposite sign. So I'm going to be subtracting. And then I do sine of pi over 4, sine of pi over 3. And now all of those values are on your unit circle. The cosine, remember, I'm doing these like you know your unit circle well. I'm moving fast. If you don't know it well, go do more flashcards. You've got to know it well. Cosine of pi over 4 is going to be a root 2 over 2. Cosine at pi over 3 is 1/2. Minus the sine at pi over 4 is also root 2 over 2. But the sine at pi over 3 is root 3 over 2. Now we go ahead and multiply those together. That's a root 2 over 4 minus a root 6 over 4. And since they have a common denominator, I would go ahead and merge those together. Root 2 minus root 6 all over 4. Okay, that is the exact value. So I could check it. I'm not going to take the time, but if I were to type this into my calculator in radian mode, whatever I get there would be the equivalent of what this would equal here. I just have it as an exact answer here versus a decimal. Okay, that's what we're doing today. Let's try a few more. So we're going to work with tangent this time. And we're going to do something that adds up to 11/12. So I'm thinking like 6/12 and 5/12, but 5/12 won't reduce. What will add up to 11, but both of them would reduce? Now, there is not one right answer here. You can do different things, and you might do it in a different order than what I do it. Like I'm thinking, how about 3/12 and 8/12? Those would both reduce, and that would add up to an 11/12. Which one you do first doesn't really matter. Now, I'm going to say this, so if I'm going to do it over here on the side, it's a 3/12 plus 8/12. Okay, that would reduce to pi over 4 plus, and an 8/12, 4 goes into both, that's a 2 pi over 3. Now, my hint here is to avoid root 3 over 3's in tangent. Now, remember that root 3 over 3's happen at all the 6. So if I use these two, I would be avoiding the 6. Now, we can't always avoid the 6. Sometimes you're just stuck with it. But if I can, I'm gonna. And you'll see why here in a second, why that's my hint. I'm going to grab these two right here. So this is going to be a pi over 4 plus 2 pi over 3. Now I'm using my tangent identity. So the tangent identity says take tangent of the first, keep the sign, tangent of the second, over 1, change the sign, and then it's going to be those two tangent values, pi over 4, but this time multiplied, tangent 2 pi over 3. All right, so tangent of pi over 4 is 1, plus tangent at 2 pi over 3 is a negative root 3. In the denominator, I have a 1 minus, and it's those exact two numbers I just wrote multiplied together. So I don't rethink it all. It's just going to be a 1 times a negative root 3. I should have mentioned to write small here. I didn't. This gets a little bit lengthy, and where it gets lengthy is right now. It's like, that didn't seem so bad, but it's all the rationalizing. And so I'm left with a 1 minus root 3 over, that turns into a 1 plus root 3. Now, right here is why I'm suggesting you avoid root 3 over 3 if you can, because then this is a root 3 over 3. So then you also have fractions caught up inside of fractions, and that becomes tedious. You got extra simplifying to do. So I'm going to try to avoid it if I can, but I cannot avoid having to rationalize. So I'm going to have to take this times its conjugate, multiply or FOIL, I guess, on the top. I'm going to have a 1. Outer is a negative root 3. Inner is a negative root 3. So that's a negative 2 root 3. And last is a negative times a negative, so that's a positive. And root 3 times root 3 is 3. In the denominator, I'm multiplying conjugates. That's very intentional. The first gets me a 1. Outer and inner cancel. And last is going to be a negative 3. And I just got rid of that radical there. In my numerator, I have a 4 minus 2 root 3. The denominator is a negative 2. And just when you think you're almost there, there's more reducing to do because I can reduce here and here. So 4 divided by negative 2 divided by negative 2 is going to be a plus root 3. So for as messy as it is to get there, tangent actually plays out pretty nice typically. Even if you end up with the root 3 over 3's, it comes out nice typically in the end. You just have to power through those fractions inside of fractions. All right, let's look at a different type of problem. Still going to be using the sum and difference identity, but not off of actual, like, I'm not going to give you the angle. Instead, we're just looking at comparisons of angles. So finding the exact value when it's not on the unit circle. So let's say that we have some angle alpha that's not on the unit circle. We know the sine value is 12/13. We know that it is in quadrant 2. But then we have a second angle. We have angle B, beta. And we know that its sine value is 3/5, and it's in quadrant 1. All right, when they give me this type of a scenario where they're kind of giving this fraction, telling me what quadrant, that typically means I need to go draw a picture. So that's what I'm going to go do right now. I'm going to draw this out. So this first one is in quadrant 2. So it's over here. And then you draw that triangle, you drop it straight back to the x-axis. And I'm looking at this like this is alpha right here. And the sine of alpha is opposite over hypotenuse. And we would do Pythagorean theorem to find the other side. You're going to learn pretty quickly that this 12 and 13 create a Pythagorean triple, which is nice. That makes life easier. So this is a 5, 12, 13. However, the reason I'm drawing that triangle out is because I have to pay attention to the signs on this. Because it's in quadrant 2, this 5 is actually negative. And I wouldn't really recognize that when they tell me the sign is positive. I might automatically think everything's positive, but it's not. All right, let's do it over here for beta. Beta is in quadrant 1. And the sine is opposite over hypotenuse. And this looks like another Pythagorean triple. The other side will be a 4. It is first quadrant, so everything is positive. Okay, so now I'm going to be using the fractions created from this to find the exact value of sine and cosine. So follow the pattern. Now, I'm going to write it like this. It's sine of alpha cosine beta plus cosine alpha sine beta. It is not the sign of a fraction. Notice here, some people want to write sine of 12/13. No, 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 no. It's the sign of alpha that equals 12/13. So what I'm doing is I'm replacing the whole sign thing with the fraction. Don't have the sign with the fraction. It is the fraction. So 12/13. And then I go over here to beta and I look and see what would the cosine be? Well, that's adjacent over hypotenuse. That's 4/5. Plus, now let's do cosine alpha. That's over here. Back over to alpha. Cosine is -5/13. And sine of beta, we're back here, opposite over hypotenuse. Actually, they gave us sine of beta, 3/5. And now we're just going to multiply our fractions together. So this is 48 over 65 plus a -15 over 65, which is going to get me 48 minus 15 is 33 over 65. What we're finding here is that if you were to have taken, and I didn't draw my angles accurately at all, but if I were to take this angle here plus this angle here, I probably would have landed, I guess they were small enough, I would have probably still landed up here in the second quadrant, because notice that the sine value is still positive. So that's what's happening, is that when I added the two angles together, I landed here in that quadrant, and this is the sine value. Okay, let's practice one more time with cosine. All right, so our cosine identity says take the cosine, and I'm writing it just so that you don't do that goofy thing with that cosine with the fraction. I'm going to write cosine alpha, cosine beta. Also, if I'm writing it, I'll be more inclined to remember it later. Change the sign. Sine alpha, sine beta. All right, now I replace all of those with fractions. Go up to my triangle, the cosine of alpha, that's adjacent over hypotenuse, -5/13. Cosine of beta, adjacent over hypotenuse, 4/5. Minus, now I do the signs, the sine of alpha, opposite over hypotenuse, times the sine of beta, opposite over hypotenuse. Now let's multiply those together. I'm going to have to go to the right. I ran out of room, sorry. So that's going to be a -20 over 65 minus 36 over 65. Already have the common denominator, so that's handy. That happens a lot. And I'm going to end up with 16 over 65. No, I am not. Nope. I missed that those were both negatives. So both negatives gives me a -56 over 65. All right. What do you think? All right, let's try one more thing. All right, here's our last slide. So this is the third way that we use these sum and difference identities, and it's to go back to verifying, where we have to make the left side equal the right side, but using our identities to do it. Now this actually is pretty straightforward. It just falls in your lap. It doesn't take a whole lot of remembering all of your identities. You kind of run it through the sum and difference identity, and then it just lands there. Okay. So here's the status. Here's your to-do list. Write the left side using the sum or difference identity. So right here, remember, we will never, never, never distribute. Instead, you replace it with the identity. And then evaluate any terms that you can from the unit circle. Since I have this pi over 2, something's going to come out that I can actually put a number in for. And ideally, terms will begin to cancel out. If not, you probably ought to go check. Okay, so I'm going to do the cosine identity with this. So the cosine identity says to take the cosine of the first times cosine of the second. Then you change your sign, so this will be a plus. Now do sine of the first, sine of the second. And somehow or the other, that's supposed to equal sine x. Now remember, you're verifying, so I got to see all the steps. None of this is mental math. This is all showing me step by step how it plays out. So that means right here, when you notice there's a cosine of pi over 2, and you're thinking, well, heck, isn't cosine of pi over 2 just 0? Then you would take a step to show me that. So I have cosine of x times 0 plus sine x times, oh, here's another one, sine of pi over 2. We know that. That's just equal to 1. And then, as I mentioned up there, hopefully things cancel out. Well, this is just 0 and goes away. And this is just sine x equals sine x. And you've got it verified right there. All right, go give your homework a shot. Good luck.